Today I'm going to talk about gear geometry. So what you see on the left-hand side here is a pinion that is called the driver. So we have a gear set now. We have a driver and we have a driven. So this is the gear. So it's pinion and gear, or driver and driven. So the gear and the pinion, they rotate because they are externally engaged. So they rotate in opposite direction. So for example, the pinion rotates in this direction and the gear rotates in this direction, okay? What you see here is like just one tooth on the gear, and here another tooth on the pinion. In this case, when the pinion starts to rotate, it engages with the gear at some point. So there is a starting point for this engagement, which is denoted as point A. And then there is a point where they disengage, and this is denoted as point B, right? In between, there is another point called P, which is called the pitch point. So at the top here, if you look at the pinion, we have, or we represent the pinion or this gear with 4 different circles. The top circle that touches the tips of the teeth is called addendum circle. And the next circle, which is imaginary circle, it's called the pitch circle. So the pitch circle is a circle somewhere between the tip and the root of the tooth. The base circle is quite important, if you remember from yesterday, because the involute curve of the tooth starts at this base circle, and the last circle, which is goes with the root of the teeth, is called the addendum circle. The pinion is represented by these 4 circles, and also if you look here, we have corresponding 4 circles for gear as well. So pinion and gear, or driver and driven, right? So this line of action, it is a line that goes through the pitch point B, okay? And also it is tangent to the 2 base circles. So at this point, the pressure line is tangent to the base circle of the gear. And at this point here, this pressure line is tangent to the base circle of the pinion, right? It is defined as the line of action or pressure line because the forces between the 2 teeth happens along this line. They push each other, the 2 teeth, the pinion teeth and the gear teeth, they push each other along this line. On the right-hand side here, you will see like another graph. It's similar to the one on the left, but with less details. You see here that we have the pressure line, and there is an angle between the pressure line and the horizontal line, this angle called the pressure angle. There are some standard values for this pressure angle, and the one that we are going to use is 20 degrees. You see here, so we have the pressure angle, the pressure line, and then we have the starting of engagement, point of starting of engagement is A, and the point for the end of it. So we are going to go for an example now. So the example says we have 2 meshing gears of 4.5 module. So the module here is given as 4.5 millimeter, have 24 and 33 teeth. So the pinion, we have pinion, this is the pinion, so this is 24 teeth and 33 teeth, sorry. The pressure angle is 20 degrees. Again, the pressure angle, if you draw a line here that goes through the pitch point, and this line here, the line of action or the pressure line, the angle here phi is 20 degrees. And each wheel has a standard addendum of 1 module. So the addendum, small a is 1 module for the pinion, and capital A is equal to 1 module for the gear. Okay. So find the length of contact. So this is LAB. Okay, and then also it asks us to find the maximum sliding velocity if the speed of the pinion is 120 RPM. So the N here is equal to 120 RPM for the pinion. Okay, I'm going to introduce the concept of, or the definition of, the maximum sliding velocity when it comes to part B. So what we have here, again, we have the module as 4.5 millimeter. We have the number of teeth on the pinion as 24, the number of teeth on the gear as 433. The pressure angle is given as 1 millimeter. The addendum is 1 module. This is not 1 meter. This is 1 times the module, which is 4.5 millimeter. The angular velocity of the pinion is 120 RPM. So what we are going to do now, in order to find the length of contact, LAB, there is a procedure we need to follow. So we're going to learn together here how to find the length of contact, LAB, right? It is mathematically involved, but you will just see that after that, you will find that it is not that difficult, actually. So here you see on the left-hand side, this is the pinion. On the right-hand side, this is the gear. And then there are 3 circles here, 3 important circles where we represent our pinion or gear. So in the pinion, on the pinion here on the left-hand side, we have R sub B, which is the base circle. So this is the radius of base circle where the conjugate part or the involute part starts. We have here R, which is the pitch circle radius. And then we have here RA, which is the addendum circle that goes along the tips of all the teeth on the pinion, right? On the right-hand side, you have capital R sub B, which is the base circle radius of the gear. You have capital R, which is the pitch circle radius. And you have capital RA, which is the addendum circle radius, right? So what we need to do now, next, we are going to draw a line. This is the line that is perpendicular to the center distances line. So we have the center point here for the gear. We have the center point here for the pinion. Then when you connect these 2 lines together, so this is the center distance, right? Then if you draw a line that is here in the middle, this line is perpendicular to the line of centers, and it goes here through this pitch point B, okay? And then we are going to draw another line that is the line of action or the pressure line, okay? So this is the line. So this is the second line. Is the line of action. The line of action here is tangent to the base circle of the gear, right? And the angle between these 2 lines is the pressure angle 20, right? So what's next? So we want to define the point where the engagement starts, which is point A. And then we want to define this point where the engagement ends, okay? So this is point A and point B. So if you remember, the point A is when this addendum circle here intersects with the pressure line. So it intersects with the pressure line at point A. And then this point here, where the second addendum circle intersects with the pressure line. So this is the end of the engagement or the end of the meshing between these 2 gears. So this is how you define point A and point B. So the first point is to mark the pitch point B, okay, which is here. Then this pitch point lies on the line of centers between these 2 centers, okay? And also it is the point where the pitch circle on the pinion and the pitch circle on the gear, they are tangent, okay? Then the second point is to mark the points of tangent. We have another 2 points here, point called A star and another point called B star. So the A star is that you construct a line between the center point and perpendicular to this line of the pressure line or the line of action. So from here, you construct a line that is perpendicular to the line of action. So at this point. So it will intersect at the point here where we have the base circle, and it is called A star. Then you construct another line from here, from the center point. It is perpendicular to the line of action. Let me just show the line of action. It's different color. So here is the line of action. Okay. You see here, this line again is perpendicular to the line of action. And it touches here at this point. It intersects the base circle. So this is the base circle. So at this point, we have B star. So this is the P star, and this point here is A star. And these 2 points are called the points of tangency, or the points of tangent, okay? Then you need to mark point A and point B. So point A and point B, as we've said earlier, they are defined based on the intersection between the addendum circle and the this green line, which is the line of action. Okay, so the intersection of the common tangent and the addenda circles marks the line of contact. So the line of contact here is between point A to point B. So between point A to point B along the this line, the pressure line here from point A to point B, this portion here is called the line of contact. Okay, so if you just take this diagram here, or this geometry, and then take it outside like this, so you will have point A star, P star. These are the points of tangency. You have point A and point B. Between these 2 points, the length between A to B is the line of contact, and you have point B, where this is the pitch point, and you have the center point for the pinion and the center point for the gear, and you have these 3 radii for the pinion and for the gear. Okay, then this is again the same points, but maybe the figure here is a bit easier and clearer, right? So the angle between the radius of the pitch point, or the pitch circle, and the radius of the base circle is the pressure angle 20 for both. Here, this is the radius of the base circle, the radius of the pitch circle, and the angle between them is the pressure angle. So what we need to do now, we just need, based on this graph here, we need to find a relation where we can find the length between point A to point B, okay? And this is what we are gonna do next. So first, we're going to use some right angle triangles to do that, because if you remember, this angle is right angle, this angle is right angle as well. So what we can do, we are gonna try to break this down into 2 portions. So we are going to first try to find the distance between A to B, and then next we are going to try to find the distance between P to B, okay? So the distance between A to P can be found as follows. We have, if we consider this red triangle, okay, then we consider this blue triangle. If you consider these 2 triangles, you will find that the distance between point A to point P is quite simple now, because the distance between A to P is P star to A minus P star to B. So from P star here to A minus P star to P gives you the distance AP. So what is the P star A distance? P star A distance, if you consider the red triangle, it is the root, this distance here is the base, it is the root of RA squared minus R sub B squared. Then minus the distance between B star to B. So if you consider the blue triangle, you will find that the distance between B star to P is nothing but R sine phi. If you consider this angle as phi, so it is R sine phi. Then from the same triangle, from the same blue triangle, you can find the relation between RB and R. So from the same blue triangle, you find that RB is actually equal to R cosine phi. Okay, then you substitute these values here, and then you have an equation for the distance between A to B. We are going to try to find another relation for the distance between P to B. So we are going to consider the same thing, but the right triangles on the opposite side. So if you consider the red triangle here and the blue triangle, you will find that the distance between P to P from this point here to this point here is nothing but the distance between A star to from A star to B, from A star to B, minus from A star I'm gonna now go to the second part of the problem, which is calculating the velocity of sliding. So if you look at the figure here on the top right-hand side, you will find that when these two teeth for the driver and the driven, when they engage together, so this here is the point of starting of engagement. We call this point A. Then these two teeth, they keep rotating until they reach this point P, which is the pitch point. And then they keep rotating again until they reach this point, which is the end of the mesh, which is point P, right? So at the starting point here, we have two rotations, if you want, or two motions. One is rolling motion and the other one is friction or sliding motion, okay? So in this case, in order to calculate the sliding velocity, we're going to assume that one of these two gears is fixed and the other one rotates around it. So if we consider this concept that, for example, the driven is fixed and then the driver rotates around it, so you will find that at this point here, at point A, there is some sliding between these two teeth, the sliding that is shown by these kind of arrows, okay? And then at the end as well, there is some sliding here between the two teeth, right? But in the middle here, when these two teeth come to the pitch point, there is no sliding, it's only rolling, okay? So in order for us to calculate the velocity or the maximum velocity of sliding, we are gonna use this equation. There is a a derivation for this equation. There is a proof that how we have reached this point or this equation. You can just try to find out about this, but eventually the sliding velocity is equal to omega, which is the rotational velocity of the pinion, plus capital omega, which is the rotational velocity of the gear, multiplied by a distance called PC. This distance PC, we have two distances here between A to P and then from P to B. So it is the first distance is AP and the second distance is PB, right? So these two distances, we're going to compare them. If you just imagine that this point A rotates about this point B, or this point P rotates about point A. So whichever is greater, so if AP is greater than PB, so we are going to use this value or this distance as our distance PC. Why is that? Because the longer the distance, so the more sliding. So PC is going to be either this value or this value, whichever is greater, okay? If AP is greater than PP, so we're gonna go for AP. If PP is greater than AP, so we're gonna go for PB, okay? So in this case, we have already calculated both lengths, AP and BP, on the previous slide. So you'll figure out that the path of approach, which is AP, is 11.14, and it's larger than the distance PB, right? So omega in this case is equal to 120, which is the RPM of the pinion multiplied by 2 pi divided by 60 to convert it from RPM to radian per second. Then we can use the, excuse me, we can use the gear ratio. You remember the gear ratio is equal to omega divided by capital omega. And at the same time, it is equal to the ratio between the teeth, the number of teeth on the gear by the number of teeth on the pinion. So in this case, we have omega, which is here, 12.57 divided by capital omega is equal to T, capital T, which is the number of teeth on the gear, which is 33, over the number of teeth on the pinion, which is 24. So from here, we can find the value of omega, which is 9.14 radian per second. Okay, so this is the value. So now we have omega, small omega, capital omega. We know that PC is the value of AP, which is 11.14. So we can simply calculate the maximum sliding velocity. So this is a small omega, capital omega, and then the value of PC, it's 242 millimeter per second. Okay, there is a note here on this maximum velocity. As I said, the above assumes that the pinion is the driver. So if the pinion drives the gear, so in this case, the value of AP is going to be greater than BC and the PB, and in this case, we are going to use the distance BC as AP. Then if the wheel drives, if the wheel is the driver, so PB is going to be greater than AP, and in this case, PC is going to equal PB, okay, to find the maximum velocity. So there is some tips on the configuration as well. For example, here, if you consider the pinion at the top and then the gear at the bottom, and we consider that the pinion is the driver now, in this case. We're just reducing the speed of the gear, and then the pinion is the driver, gear is the driven. In this case, you see here that what happens in this case, the contact on the pinion is going to be towards the tooth root. So if this is the pinion at the top, and this is the teeth, the tooth of the pinion. So the point of contact here at the beginning is going to be towards the root of the tooth of the pinion. And for the wheel, the contact on the wheel is going to be at the top, at the tip of the tooth. Okay, so if you look at this point here, consider that this is this one here is the tooth for the pinion, and this one is the tooth for the gear. So the contact is going to be towards the root for the pinion and towards the tip for the gear. So if you consider that the wheel or the gear drives, so the gear is here, okay, and it is the driver. So at this case, if this is the tooth on the gear, so the contact starts here. So the contact in this case at the pinion is going to be at the tab, but the contact on the wheel is going to be towards the root, as you see. So this point here, okay. Right, so you need to just figure this out more. You just need to draw it and then focus on this happening, okay?